Hello friends, my name is Vivek Sharma. Today we can cover this interesting problem that's called flatten a multi-level doubly linked list. So in this problem we have been given a multi-level doubly linked list and we need to flatten this. Okay. So what we will do, we will try to understand from this diagram on the whiteboard. So here we can see like there are three levels, right? 1, 2, 3. So these are three levels. And how these three levels are coming into the picture, we will also try to understand that part as well. Okay. So here normally the doubly linked list basically having two pointers only, right? So if we have to see the doubly linked list, right, then it will have basically, let's say our doubly linked list having these two boxes, right, these two nodes, then generally it will have only two pointers. One is previous and another is next. So these two doubly linked list, these two boxes will point to each other. So that's basically basic structure of doubly linked list. But in this case they have another pointer that's called child here as well. Okay, and due to this child node we are having the multi-level. So child is having like down to this node and another child will having down to this node. So that's why we are having three levels here. So now how we will be flattening that, that's the second part, but let's try to understand this problem a little bit. Okay, so basically what we need to do, we will just traverse through from here 1 to 2 and then 2 to 3, and we will check, okay, we got the child, means we will go to the down level, and then we will check, okay, next is not null, then we will traverse through here and we will check here, okay, child is not null, then we will come here and then we will come here, and then this is the end. Okay, but the story does not end here. What we need to do now, we need to connect this node here and then we need to connect this node here as well. So how we are going to connect these nodes, that's the second part of the problem. That's the solution part that we will be looking into it as well. But here let's see that these are the parts that we need to store somewhere, right? Definitely if we don't store it basically, then we cannot connect these parts, right? So that's how we need to flatten. So what will be the flatten linked list here? So it will be 1 2 3. After 3, so let's connect these as well. 1 2 3. After 3, 7 will be coming. Okay, and then 8. After 8, 11 will be coming as per these red arrows, and then 12 will be coming, and after 12 these 9, and then 10, and then 4, and then 5, and then 6. Okay, so this will be our flattened doubly linked list in the single level. So how did we accomplish this linked list basically? So we started from here, and then once we found the child we came here, we again went to right side. Once we found the child we came here, and then we came here, and then the remaining linked list we came here, and then after that we came here. So that's the basically pattern that we followed here. Now quickly we can see here that how we are going to solve this problem. So definitely we know that this is how we are going to so let's write down here again 3 7 8 11 12 9 10 4 5 6 4 5 6. All right, so this is our flattened doubly linked list, right? 1 2 3 7 8 11 12 9 10 4 5 6. Very good. So that's what the problem is. Now let's coming to the solution part, how we are going to solve this problem. Okay, so now let's move to the fresh diagram here. So one observation is still clear. We are just going through each node by node. Once we are finding child is not null, then we are going to the child node. If we are finding child is null, then we are not caring about the child. So this observation is pretty clear. Okay, if child is not null, then we are basically going down, means we are assigning this next value to the child. Okay, so otherwise the next is having like this previous or next, right? So this is the structure, right? So each node is pointing to each other, but here the child is also there, right? So let's say this guy is having child here downside, so this next will be pointing to the this pointer. Let's say this is the node, right? So then this next will be pointing to this, okay, considering this is the child. So that's what we are going to do here. So in this case, what we will be doing, this child, so this next will be pointing to the child. And what is child here? This. Similarly, this next will be pointing to the child, this child. Okay, and this next, because it's end of the structure, right? Then in that case, we need to store these guys somewhere, right? 4 5 6, right? And then we need to connect these structure as well, 10 and then 4. So this is the second part of the problem. First part of the problem is basically when child is not null, then store this next to the child, right? And also store this somewhere. Now let's think about the data structure as well, which data structure we are going to take here. So if you see here, from the down we are taking the down array, down this level. We are not going to connect 4 to the 12, right? We are going to connect 9 to the 12. What does that mean? That means that we need to go from bottom. And what is this structure called? Last in, first out. Means whatever is the last is there, that should come first. What does that mean? That means the stack data structure, right? So whenever we are traversing through, once we found child is not null, let's put only this node to the stack. We don't need to put 5 and 6, right? Because once you will put 4, 4 is already connected to 5, 5 is already connected to 6. We don't have to worry about the whole boxes after 4, right? Once we store this 4, that means that other connected nodes will already be there once we will access 4 from the stack. And again, on the second level, we will again store 9. So now stack will have this thing, right? 4 and 9. And once we will go to the 12, then 9 will be on the top of the stack. We will pull this, we will pop this from the stack, we will connect from this 12, okay, and now then we will traverse through 9 to 10 because it's already connected. Once we found next is null again, then we will again connect pop 4 from here, and then we will connect 4, and then we will traverse through 5 and 6, right? So that's what exactly we need to do. So let's do this. Let's quickly note down our notes. One is basically we need to check if child is not equal to null. Let me take different color. So if child is not null, right? Once it is not null, store or basically update node dot next equals to child. Okay, this is very simple to understand our problem. So if child is not null, then update node dot next equal to child. This is the one learning that we had. Another learning is basically store next to stack. Okay, so store node dot next to the stack. Why? Because to handle this situation that we have seen, right? And if node dot next equals to null, what does that mean? That we went to the end of the node, right? We came now to the end of the structure. If node dot next equal to null, then assign next to stack dot pop. That's what exactly, that's only these steps, right? So we will see here basically whenever we found next is null, right? Whenever we found next is null, what does that mean? We need to pop from the stack and we need to assign this next to here. Similarly, next is null, and if stack is not empty, then we need to pop from stack and we need to assign it here. So that's what exactly we noted here, right? So if these steps are clear, code is pretty straightforward, right? And these steps we make sure that we are understanding these correctly, right? So child, if child is not equal to null, then basically then assign this next to the child and store this node, further node to the stack. Similarly, child is not equal to null, then assign this next to the child and store this node to the stack. So in this way, like 4 and 9 will be in the stack. Once we found next is null, what does that mean? If next is null means we came to the end of the structure, end of this whole structure, right? So next will be only null in that case, right? If you see here, this is next is null, right? This next is null means it is the end of the that particular label, right? This doubly linked list, this label is ending here, this label is ending here, this label is ending here. But because child is there, right, because of the child we came to the uh, down stair label and to the down stair label, right, with the help of the child. So then first next will be null, would be signaling us that this is the end of the structure, and in that case we will pull from the stack and we will assign this, right? So this is pretty straightforward. Another additional item we need to do, we need to take care of the previous as well. So once we will do this, we need to assign this previous as well. That's the pretty straightforward thing. So let's convert quickly this idea to the code here. So what we can do here, we can take one current node. What this current node does basically, this current node basically we are storing, we are taking one pointer. So we don't want to modify, we don't want to move this head pointer, right? So if our head pointer is 1 here in this case, right, and if you will keep moving this head pointer from here, 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 what we will need to return in the last, in the end of the algorithm, right? This head pointer will come here, and then in the end head pointer will be pointing to here, right? So what we will return to the head, right? If we have to return the head, we need to store this guy somewhere. And then with the help of temporary pointer, current pointer, we will move this current pointer here and there. And then once all this structure will be flattened, right? Once this structure will be flattened like this, then we will again return the head pointer, so that this head pointer will be connected on the single label, right? To flatten this multi-level doubly linked list. All right, so let's go ahead and do this. So while this current, if this current is not equal to null, then what we are going to do here, we have learned so far two conditions here, mainly two conditions. One is the child is not null, that's one condition. Then we need to update the node dot next to the child. And another is basically if no node dot next equals to null, that means it is the end of the node, right? This is the end and this is the child condition. So these two conditions are main, right? And in fact we can modularize to the third condition is basically if these two are not there, then we need to simply traverse through, right? What does that mean? That means is basically, let's say if like this scenario, right, 1 to 2, child is not null, next is also not null, right? Or we can just move to little cleaner diagram. So in this case next is not equal to null, we just need to move current equal to current dot next. In this case also current equal to current dot next. So that will be the by default step to traverse to linked list, right? So current equal to current dot next, that will be the default traversal through traversal. Now if current dot child is not equal to null, what does that mean? We need to store stack. Oh, we need to take stack as well here. So stack node stack equals to new stack, and we need to store current dot child, in fact current dot next, right, not the current dot child. Why? Because once we found this situation, we need to store this guy. So we need to store current dot next to the stack, right? So we will be storing 4 here, and then we will be changing current dot next equal to current dot child. So let's go ahead and do that. So current dot next equals to current dot child. All right, and because this is doubly linked list, so we need to change the previous pointer as well. So current dot child dot previous equals to current dot next. So current dot child means this guy, and then this previous will should be pointing to this node, not the next, but the current dot previous should point to this node, right? So I made a mistake in the code, I will correct that. So just remember that this previous should not point to the next, right? If it will point to the next, then again it will point to this node that we don't want to point, right? So just be careful that we are pointing to this whole node, not the next, not the previous or nothing, right? So here we need to point current.child.previous to the current, right? So this is pretty obvious, right? Pretty obvious we will be pointing this whole structure, but it's if we don't use any observation, then by default or by error, if we will point to the next, then next again pointing to this, and that will be wrong. So we don't want to do that. All right. Now the second condition here is if current dot next equals to null, right? What does that mean? If current dot next equals to null means this situation. And also make sure that stack is not empty, so that we can assign this to the from the stack, right? But in fact this case, like 9 will be there on the top of the stack, so we can assign basically this guy 9 here, right? So if a stack is empty, then there is no use, right? For example, if we will come to here and stack is empty, then what we will do? So we just need to make sure that stack is also not empty. So stack is not empty, right? Stack dot is empty, not, right? So it is, if its stack is not empty and current dot next equals to null, then what we can do, we can take this node equals to stack dot pop, and then current dot next equals to node, right? So we can assign this node to the current dot next, right? And again node dot previous we can assign to the current, not the current dot next, but to the current, the whole structure we just saw here, right? So current dot previous, it will go to the whole structure, this whole node. All right. Another important point here is, let's say stack, because uh, we are blindly storing this next part to the stack, right? And stack can be null as well, right? Right? It can be null. So we just need to make sure that we are, if it is null, then we are not assigning to this guy, right? So node should not be null. It should not be null. And in what case it might be null? Let's see that case as well. Okay. Let's say we are having these nodes, right? So these are two nodes. Let's say, for example, current dot next is null and it's having the child as well, right? I mean, some hypothetical example. And basically with the previous steps, it's having like multiple structure here and there, and earlier stack was not empty, and then we reach to this stage where stack is empty, and now this guy is null and child is already there, right? And then basically we assign to the child, or maybe basically if even if the child is null, let's say this example, right? Let's say you are having only one node, so this is null, right? And this is null. So if you will assign current dot next equal to child, it will not complain. But if you will do this null dot previous equal to child, it will complain, right? So I just simplified a bit to understand this, right? So we just need to make sure that this next is, this node is not null basically, right? Or another way to handle this is basically we have null check here. So if current dot next is not equal to null, then only we assign, then we don't need this check, right? Either way we need to handle, right? So anyways, we can handle this in whatever the manner we want. So I think we are done here. Another important point here that I missed intentionally, that we are changing these pointers, but we are not freeing this memory, right? So even if we are pointing this next to this child, we are pointing this next to this child, but this child is still pointing to here, right? This child is still pointing to here. So in that case, what will happen? In that case, this will not be flattened, right? So let's try to see this guy, and in the end, let's go ahead and return head because we persisted this head. So the linked list is not a valid doubly linked list, right? Why it's coming here? Because child is still dangling. Child is still dangling here and there. And the expectation is when we want to flatten, we want to free this child should be null, right? Otherwise, how this multi-level is the like different structure when we need to convert this to the doubly linked list, simple doubly linked list. So current dot child, we should free this pointer here, child equals to null, right? So in that way, what we will do, we will disconnect these connections, and we will connect with this, right? That's what exactly we will be doing. Okay, all right. So let me undo couple of things so that it will not be messy. Okay, so now let's see here. So now this looks like fine, right? In terms of the complexity here, time complexity will be the order of n, because we are traversing each and every linked list. And space complexity here, basically, let's say in the worst case, this stack we need to store like most of the nodes, then it will be the linear as well. However, we can argue that it will not be in the best case or the average case, it will not be the order of n or the linear complexity. And the reason of that is basically, if we see like this kind of the structure, right? This is this kind of the structure. Here we are just storing like these two nodes, and there are many nodes, right? So we can argue that it will be the less than linear. But let's say like we are having some kind of the structure like some weird case, right? Some this kind of the structure where next is also there, and null is also, next is basically null, but basically every next is also there, right? And child is also there, so it's connecting to the child here, right? It's connecting to the child, and it's connecting to the null. It's connecting to the child, and it's connecting to the next as well. So in that case, basically we still need to store 3 nodes in this case to the stack. So it really depends like what kind of structure we are getting. So we take like very now in the worst case scenario, it will be still be the linear or the order of n. So we should consider all the worst case as well. So I think this is looks fine. Let's try to, so it already compiled, and let's try to quickly submit, and let's see if it is working. So it looks like this concept is working fine as per our assumptions, and as per our understanding. So before ending this video, just a quick summary. This is like multi-level doubly linked list that we have been given, and here we need to give additional pointer that's called child here, right? We have been given the child, this pointer, and with the help of child, it's getting to the multi-level here. So what we need to do here, important observation is we need to get rid of this child. We cannot structurally we cannot get rid of the child. So what we need to do, we need to assign this next to the child node, right? So that it will be flattened at the single level, right? So if we will go to the very first page, and then if we will see this flatten doubly linked list, right? So we flatten this doubly linked list, multi-level doubly linked list to the single level, right? How we did, we basically change this next pointer to the child pointer, and child memory, don't forget to free this memory, right? And then once we do this, at the same time we need to store this to the stack as well. And what is the intuition to get the stack? Because if we will reach here, we will see, okay, we need to store now 9, not the 4, right? So we are going bottom up approach here. We are going from bottom to top. And which data structure provides this facility? That is last in first out, and that is the stack, in other words, right? So then if we will store like here 4 and then 9, then basically after 12 we will be getting 9, and that's why we are taking the stack here. So that's pretty straightforward, and once we will understand from this diagram, then I think we can conclude these points. Like if child is not null, then we need to update node dot next to the child and store node dot next to the stack, right? And the second point is, if node dot next equals to nulls, means it is the end of the structure, then assign next to the stack dot pop. And we need to carefully assign this previous as well, right? So current dot child dot previous equals to current, because it is the doubly linked list structure, and that is important point, right? If we don't free this memory from the child, basically if we don't free this memory, then it will still be dangling, and that we don't want, basically. So we don't want to dangle this pointer here, we don't want to dangle this pointer to here, so we want to disconnect this link here. That's why we are freeing this child memory as well. So hopefully this might be useful to build understanding and to understand the code. Thanks a lot. Have a good one. Bye.